So as a first example, let's solve Laplace's equation on an annulus, which is the area between two circles. So given a circle of radius r1 and a circle of radius r2, we're solving Laplace's equation on the area between the two circles. Okay, so that's an annulus. So you guys agree that this is a perfectly well-stated problem. We have a domain, so it doesn't have two boundaries. It has one boundary, but the boundary has two parts. So you have to specify a boundary condition on each part of the boundary. And on the inside, I'm saying it's cosine theta plus cosine of 2 theta. It is a Fourier approach. I just don't want to do an infinite Fourier series. So that's why I'm only throwing in a couple of Fourier terms. And on the outer boundary, it's 2 cosine 2 theta minus cosine of 5 theta. Okay, now I'm going to go with one of my ploys of trying to say something wrong and see whether you can tell me what I'm saying wrong. And in this case, it's more silly than usual. So you'll see what I mean. So we kind of know what the solution looks like for radial shapes, radially symmetric shapes. It looks like this in polar coordinates. It is a sum, and I will write a complex sum just because this way I only have to write one summation instead of 3 different terms for cosines and sines and the constant term. But then, of course, when we do this, we'll just use this. The Fourier series is already presented in real terms, so might as well use it. If you're still not 100% comfortable with complex numbers, then just think of a sine and cosine series. It won't matter. We're just talking. And so I'm looking in this, and I'm sensing trouble. Because I'll tell myself, well, first I'll match the outer boundary conditions. I'll match the outer boundary conditions. So by plugging in R2 into this series, and then whatever I get here, that will help me determine the coefficients uniquely. You guys are with me? And then I'll try to satisfy the boundary conditions on the inner part of the boundary, and oops, I'm out of coefficients. So it seems like there's a problem. So you'll tell me in a moment what the problem is, but there shouldn't be a problem. Because I said what I said before, I said it for a reason. We have a perfectly normal domain, very nice, very symmetric, very regular, very smooth. So just because it has 2 parts to the boundary shouldn't break the paradigm of partial differential equations. The paradigm being that if you state Laplace's equation and you assign boundary conditions on the boundary, there is a unique solution. And all of a sudden here, we're not able to match both boundary conditions. So in the current form, you guys agree there's a problem? Who can tell me the solution? What silly mistake am I making? Exactly. Remember when we separated our variables, there was the angular part that just gave us sines and cosines. And then there was, angular, I said it right. And then there was the radial part, which gave us r to the n and r to the minus n. And we said r to the minus n doesn't work because we were doing it on a unit circle. That blows up at the origin. So we rejected them because all of those blew up at the origin. But here, we don't have that problem because the origin is not part of the domain. So we can use r squared and also r to the minus 2. And also r to the 5th and r to the minus 5. So r to the 5th schematically might be look like this, right? It grows in this region. And r to the minus 5th diminishes, right? But they're both perfectly finite. No problem whatsoever with both positive and negative exponents on r. So that's where the other half comes from. So let's actually bring this problem to completion. And I'll just write basically what the solution will look like. Because we know the paradigm, we know the framework. Decompose the boundary conditions into Fourier series, where we've already done that. It was done to begin with. And then multiply each one by the corresponding r to whatever power. So this is what the solution will look like in this case. So to satisfy the outer part, well, let me add one term, the other term, which will look like this. So we have our C's having to do with the positive powers and D's having to do with the negative powers. So here's what we're going to have here. I'll just call it C1 because it's 1 theta. So and then we will, so that's satisfied, we're good with this one also, that's already represented, so we just need 2 more here. So plus these are the ingredients that will be in our solution. So 6 unknowns, we'll end up with 6 equations. And I have my computer ready to solve them. Maybe it'll be worth the cumbersomeness, maybe it won't. We'll see. We'll try it. I think it'll be nice to see the answer. Maybe I overcomplicated these a little bit. Maybe I should have had just one of them. Okay. So first, let's plug in R2. And when we plug in R2, the answer should match this boundary condition. Do you guys agree with me? Yes, you're right. I'm not following. Should match this boundary condition. So the coefficients for cosine theta should add up to 0 because there is no cosine theta here. So plugging in R2, we get C1 R2 plus D1 R2 to the minus 1. No more cosine theta. 0. Cosine of 2 theta coefficient should equal 2. Six equations, 6 unknowns, perfect match. Maybe I should have done something a little bit simpler. Let's program them. So A equals, what's the first equation? Just give me the first 2 coefficients. So these are the unknowns. So the coefficients are R2, R1 over R2, 0, 0, 0, 0. Make sense? Because these guys, the other variables are missing. I was pointing to the wrong place. So R2 and 1 over R2. 0, 0, 0, 0. Okay, that's line 1. Line 2. 0, 0. R2 squared. 1 over R2 squared. I think I can see where this is going. 0, 0. The next line is 0, 0, 0, 0. R2 to the 5th. 1 over R2 to the 5th. Okay. Of course, all of these equations are pairwise decoupled. We could really solve 3 2-by-2 equations instead of 1 6-by-6 equation. But since we have Mathematica, why not? And then the other one is the exact same thing, the other 3, but with R1 instead of R2. So R1, 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 R1. That's A. And the right-hand side B is 0 to negative 1, 1, 1, 0, right? Okay. And the answer is A, inverse of A, inverse of A times B. And here it is. Oops. I'm sure that's correct. Can we simplify? That's not bad. Can we full simplify? Okay, but we'll do something a little different. We'll pick R1 and R2. So we'll say that R1 is 1 and R2 is 3. Should we do that, just so that it's not 2? And then the solution is just these numbers. Okay, so let's call this our C, coefficient C. Okay, so we've now got our C. So our solution, I'll put a semicolon to suppress it, U as a function of R and theta. I'll denote it by T. Even though Mathematica is very nice, I can actually create the theta symbol. I'll do it just to show off its nice capabilities. That won't do it. Isn't that nice? Equals C1 times R times cosine theta. Am I right? Plus C2, which is D1, times 1 over R times cosine theta. You guys are with me? Plus C3, which is C2, times R squared times cosine of 2 theta, plus C4, which is D2, times 1 over R squared. That's not it. R squared times cosine 2 theta, plus C5 R to the 5 cosine 5 theta, plus C6 R to the minus 5, well, we've been doing it like this, 1 over R to the 5 times cosine 5 theta. Okay? So one test that I would like to do is to plug in R2 and see what we get. So U of R2 and theta, let's see what it is. Is that correct? Okay, that's good. And for R1, we get this. That's correct. Okay, so now all that's left to do is to plot the solution. I'm sure it'll be something nice. Let's see. Well, we'll need to use, so we need to do it in cylindrical coordinates. I don't know how to do it, so I'll do a 3D parametric plot. So I'll kind of have to do the conversion to cylindrical coordinates myself. So I will say parametric plot 3D, and the x variable will be R times cosine theta. The y variable will be R sine theta. And the z coordinate will be U of R and theta, where R goes from R1 to R2, and theta goes from 0 to 2 pi. I forgot to close this figure bracket. Okay, are you guys ready to see the solution? I'm ready. Yeah, that's what it is. Thank you. So let's look at it from the top. It should look like an annulus, kind of. It does indeed. And do you see that 5 theta? You see the 5 wiggles on the outside and just 2 wiggles on the inside? Okay. And do you guys see this property of solutions to Laplace's equation? How you can kind of see it. There are no local minima or maxima. Every point is the average of its neighbors. It's actually one of the ways of solving Laplace's equation. Just putting the right values on the boundary because we know them, whatever you want in the middle, and just continually, one time after another, replace every point with the average of its neighbors. And so the information from the boundaries will begin to propagate into the interior. And it'll be sort of like a heat equation, in fact, very much related. And then you'll end up with this, the perfect averaging of all the values. Pretty cool? Okay, so now you know how to deal with annuli. That's probably plural of annulus.